Welcome to a slow, beginner-friendly lesson on using floats, made for absolute beginners. Practice storing and printing floats. No formula sheet. No science library. A quick recap from last lesson. A float is a number with a decimal point. 2.0, 3.14, negative 0.5. The dot is what makes it a float, regardless of the digits. Today we go beyond recognizing floats and actually compute with them. The good news is that float arithmetic looks exactly like ordinary math. The interesting news is that one famous detail will surprise you, and understanding it is the heart of this lesson. The dot rules. Here is the first rule of float arithmetic. When you combine an int and a float, the result is always a float. Adding 2 plus 3.0 gives 5.0, a float, not 5. The idea is that Python widens to the more general type so no fractional information is lost. Even when the answer happens to be whole, like 5.0, the type stays float because a float was involved. This rule is consistent and it keeps arithmetic honest. Widening keeps detail. Numbers come in different shapes, and arithmetic has to respect all of them. When a whole number meets a fractional one, the result keeps the fractional shape, so nothing is lost. It is like pouring a small cup into a larger bowl, the larger shape wins, and every drop is preserved. The larger shape wins. Let us see the mixing rule in code. 2 plus 3, both ints, gives 5, an int. But 2 plus 3.0 gives 5.0. A float, because a float joined the calculation. 7 minus 2.0 gives 5.0. 4 times 2.5 gives 10.0. Notice the pattern. The moment a float appears, the answer carries a dot and becomes a float. Read each line and the rule jumps out. A float anywhere means a float in the result. A float in, a float out. Let us state the rule plainly. For addition, subtraction, and multiplication, int combined with int stays int. But the moment a float is involved on either side, the result becomes float. That is it. One simple rule covering 3 operations. You do not need to memorize a table. Just glance at the values, is there a dot anywhere, and you can predict the type of the answer. Division, though, has its own rule, which we look at next. One simple rule. Division is special. In Python, the ordinary division operator, the /, always returns a float, even when the answer is perfectly whole. 6 divided by 2 gives 3.0, a float, not 3. The reason is sensible. Division can produce a fractional result, like 7 divided by 2 equals 3.5, so Python always uses the float type to be safe. If you specifically want whole number division, there is a separate operator, /, which we will glance at shortly. Slash means float. Here is division in action. 6 divided by 2 gives 3.0, notice the dot, because slash always returns a float. 7 divided by 2 gives 3.5. 10 divided by 4 gives 2.5. Now compare with /, the whole number division operator. 7 /2 gives 3, an int, because it discards the fractional part. For everyday measuring you will usually want the single slash and its float result. Single versus /, 2 halves meeting to make a whole, or something close to it. That is division in spirit. Sometimes the halves fit perfectly, sometimes a fragment spills over, and the float type is there to catch the fragment rather than throw it away. Precision is preserved, even when it is inconvenient. Catch the fragment. Now the famous surprise. In Python, 0.1 plus 0.2 does not give exactly 0.3. It gives 0.3 followed by a string of zeros and a tiny 4 at the end. Before you worry, this is not a bug. It is a fundamental fact of how computers store fractional numbers. Every programming language using floats has the same behavior. The error is tiny, far beyond what matters for everyday work, but it is real, and understanding it is the key to using floats well. The famous surprise. Let us see the surprise in code. We print 0.1 plus 0.2, and out comes 0.300000000000004. When we ask, is that equal to 0.3, Python says false. The difference is about 5 times 10 to the minus 17th, unimaginably small, but not 0. This is the single most important thing to know about floats. Never trust them to be exactly equal after arithmetic. Compare with care, or use rounding. Equal returns false. Why does this happen? Computers store all numbers in binary, base 2. Just as 1/3 has no exact representation in decimal, it becomes 0.333 repeating. Some simple decimals have no exact representation in binary. 0.1 is one of them. The computer stores the closest value it can, and that closest value is ever so slightly off. This is not Python being sloppy. It is a mathematical fact about base 2, shared by every float in every language. Base 2 cannot fit. Precision and approximation walk hand in hand. A measurement is never the thing itself, only the closest representation we can hold. Floats work the same way. They are honest about being close, not perfect, and once you accept that, the tiny errors stop feeling like mistakes and start feeling like the nature of measurement. Close, not perfect. Let us make the binary idea concrete with a decimal analogy. 1/3 in decimal is 0.333, repeating forever. You can write it down only by cutting it off, which introduces a tiny error. The same thing happens to 0.1 in binary. Its binary form repeats forever, so the computer cuts it off to fit in memory, and a microscopic leftover remains. That leftover is the 4 at the end of our surprise. Once you see the analogy, the mystery is gone. Like 1/3, the first tool for tidy floats is the round function. Round takes a float and an optional number of decimals, and gives back a cleaner float. Round of 3.14159 with 2 decimals gives 3.14. This is perfect for display, for prices, and for any time you want to throw away meaningless trailing digits. Round does not fix the underlying precision issue, but it lets you present numbers that look clean and trustworthy to a human reader. Tidy for display. Here is round at work on a real price calculation. The raw total of our earlier example is 12.0879, which is more detail than any receipt should show. We pass it to round with 2 decimals, and we get 12.09, exactly what a customer expects to see. This is the standard pattern for money in Python. Compute in full precision, then round only at the moment of showing the result. Clean math, clean display. Compute full, round late, operations pile up, and so do tiny errors. Each addition, each multiplication, can nudge a float a fraction further from the clean number you expected. Knowing the tools, rounding and careful comparison, lets you steer through that accumulation without ever being caught off guard. The float is predictable once you know its nature. Errors accumulate. You can convert between int and float on purpose. The float function turns an int into a float, so float of 5 gives 5.0. The int function goes the other way, int of 3.9 gives 3. Notice, it does not round, it truncates, it simply cuts off the fractional part. Int of 3.9 is 3, not 4. These converters are how you tell Python exactly which type you mean, regardless of how a value was originally written. Convert on purpose. Let us see the converters in code. Float of 5 gives 5.0. Int of 3.9 gives 3, the fraction is cut, not rounded. Int of 3.1 also gives 3. The converters even work on strings that look like numbers. Int of the string 42 gives the integer 42, and float of the string 9.99 gives the float. This is how you turn text input from a user or a file into numbers you can calculate with. Truncate, do not round. Here is a real-world pattern for money. Prices and taxes are floats, so you compute the total in full precision. Only when you show the total to a customer do you round to 2 decimals. And because of the precision surprise, you should almost never check whether 2 floats are exactly equal with a double equals. Instead, check whether they are within a tiny tolerance of each other. We will not code that today, but knowing it exists keeps your future money calculations safe. Never trust exact equals. One more real example, an average. We have 4 scores, 7.5, 8.0, 6.5, and 9.0. The average is the sum divided by the count, which gives 7.75. If we want a single decimal, round with 1 gives 7.8. Averages are everywhere, grades, ratings, temperatures, and they are almost always floats because dividing rarely lands on a whole number. This tiny example is the shape of a great deal of real data work. Averages are floats. Let us hold the whole lesson together. Mixing an int and a float always gives a float. Division always gives a float, even when the answer is whole. Floats carry a tiny precision error because some decimals have no exact binary form, so 0.1 plus 0.2 is not exactly 0.3. The round function tidies floats for display, and int and float convert between types on purpose. If those sentences feel solid, you understand how to use floats. 4 solid sentences. The takeaway, in one breath. Floats behave like ordinary numbers in arithmetic, and a float anywhere makes the result a float. Remember the famous precision surprise, and reach for round when you display. Use int and float to convert deliberately. That is the practical toolkit for fractional numbers. In the next lesson we step away from numbers entirely and meet none, Python's way of saying there is no value here at all. The float toolkit. Where does this leave us? You now know how to use floats in arithmetic, you understand why a tiny error can hide inside them, and you have round and int and float to keep values tidy. The next lesson changes direction entirely. We meet a value that is not a number at all, but the absence of a value, called none. Take a breath. You just finished the numeric types, and that is a real milestone in learning Python. Onward to none. Every calculation is built brick by brick from smaller ones. Float arithmetic is no different. Add one value, multiply by another, round at the end. Once you know how each brick behaves, the whole wall stands solid. The numeric types are behind you now, and that is a real foundation to build on. Thanks for watching. Next, the none type.